Is magnetization studies of high TC superconductors. This presentation is given by Professor Doug Finnemore.
I'll start off with the conclusions, in case there's any doubt. Lutetium barium copper oxide is indeed a superconductor. TC is 90 Kelvin. The samples we've made show 20% of full flux exclusion as you cool in temperature in a constant field. If you have pinning, of course, you don't expect full flux exclusion. In the yttrium barium copper oxide, we were actually working with the 327 compound, thinking that that was the right stuff. When we started this, it has TC, there's obviously a phase with TC of 91 Kelvin. It shows again 34% of full Meissner effect. And flux pinning at low fields, and I would like to spend a little time concentrating on the magnetization curves and how irreversible they are. The 40-degree superconductor is very reversible, and you can get free energy curves from that. Okay, the lutetium barium copper oxide was submitted to PhysRev letters on the 2nd of March, and it's a joint Brookhaven-Ames effort. Arnie Mudenbaugh called Bob Shelton and said that he had superconductivity in this material, and they started a collaboration with Mudenbaugh, Sunaga, Asano, Cox, and the names that Shelton, Koo, McCallum, and Clavins working on it. Now this is a 214 mixture, which is not the right mixture for this, but cooling in a field, you can see this is the first data they took. And so superconductivity onset comes at about 90 Kelvin, but not a very large fraction of the sample goes. Sort of an intriguing effect in this particular sample is that as you cool on down, there appears to be an antiferromagnetic transition, which we associate with a piece of second phase in the same material, but it's a very sharp drop. And just to complete the electrical resistance for this material, comes down, as you can see, drops to zero at a temperature substantially lower than where the Meissner effect onset comes. That's the green line at 91, and I've drawn the red line just in case you want to be optimistic. I like to define a quantity called T sub mop, which is T sub most optimistic point. The group also set out to do the 1, 2, 3 phase, and the X-ray pattern for this still obviously has some copper oxide in, still obviously has some lutetium copper oxide, and then the main phases are in black. Got 2.5 minutes? Thank you. And Arnie Mudenbaugh is giving a talk on that later tonight, all of that work. Now, the flux pinning work is done by the Ames group only, and just a quick tutorial. If you measure magnetization curves, you have the Meissner region at low field, and if in normal material like niobium 310, you'd get a large amount of hysteresis, and delta B gives you a measure of the pinning in the material, as related by the equation I showed there. If there's no pinning, you get the free energy, and if there is pinning, you get the JC, and so it's valuable whichever way the result comes out. And in the lanthanum strontium, it's extremely reversible. And 4 pi m is a function of h. The open circles are increasing field, decreasing field, and you can get the free energy out of those data, and it's published Rapid Communication April 1. You can look all those data up. In the yttrium barium, we had great joy from the Bell Labs group in 1100 amps per square centimeter. And the sample I'm going to describe for you was actually this 327 sample, which goes at 91 Kelvin. Lee G took these data. These are AC susceptibility. I assure you these are not arbitrary units. It really is 34%. The machine's calibrated. And the same sample, if you exclude flux, as you cool down, it does indeed exclude flux. That's no surprise. But what I want to show you is the pinning. So this is a magnetization curve at 10 Kelvin, which is pretty low temperature. And if you take the point at about half a Tesla, you get 96 amps per square centimeter. But I would like to point out as you go up to 2 Tesla, which is still a very small field, the pinning goes away. So saying things happen at 0 field is not a good indication of the practical use of this material at higher fields. The pinning really gets much smaller. And if you go to 78 Kelvin, it's even less friendly. It's much more reversible. And at 78 Kelvin, increasing and decreasing fields. So that I think we're going to have a lot of hard work. Now, the worry is that we have weak links between grains. And I think we should focus on these weak links between grains. Thank you.
Thank you, Doug.